You still hear us? That's a connection lost, but it might be on his end.
Oh.
Okay, I think you started the recording and or something got blocked because of that. I think you started the recording and it mute me and he removed the video and he said that you need to agree, you need to press OK to to continue. But it wasn't showing me on the slide I was presenting, so probably I lost you some time ago.
You receive a prompt on the screen.
No, I do not receive anything. We did not record, so nobody touched.
Okay. Like you were muted for 20 seconds roughly.
Okay.
We can't see the presentation anymore.
Yeah, we can't see the presentation.
Stop sharing. Let me do it again. Not a problem.
Now it's back.
Yes. So thank you.
You can see it? Okay. So I was just saying data structure before circuits. I think I made that point. Lattice, blocks, and operations. And yes. And I think Steam did the right thing here. Leaving people the freedom to build circuits however they want. It's a simulator. So Gitney did not force people to overthink all of this, but we think that it makes sense to have a data structure sitting on top of the circuit level. Now, looking back at the ECA, I'm starting to introduce the memory experiment. So you have a lattice, you have a bunch of cycles, you create a rotated surface code, you instantiate your blocks, in this case is only one, and I have operations. Reset all data qubit, you measure the syndrome, and you measure the logical Z at the end. This is the definition of a memory experiment. So you instantiate your logical qubit in zero, logical zero, so in logical Z, and then you measure it at the end, and you expect it to be the same. And then you interpret it with the ECA. So the idea is that, of course, you will need to have some kind of API that allows you to build these blocks in a nice and simple way. So here on the right, we see an example of how we build such a block for the repetition code. So you see there is some lower objects that you can use if you're interested in, stabilizers, Pauli operators. And here is the definition of a block. It has a label, it has a set of stabilizers, you have a ZZ, and you have some indices on where it acts, and you also need to specify where the ancilla qubit is going to be. And likewise, for the second ZZ stabilizer, and then you define the two logical operator, the logical X and the logical Z. This is just a repetition code, but the point here is just to show that you can define these objects. So yes, and we will see more example of this in the demos afterwards. Third part, the operations. All codes that we support come with a bunch of operations that are available throughout. We think these are pretty general. The measure syndrome, the reset data syndrome, the measure for the logical XYZ, because you always have those definitions, the application of the logical XYZ, because again, if I define a logical qubit, I know what XYZ look like, so I can always apply those operators. State injection and conditional logic. That's important for lattice surgery. Get back to it after. For the rotated surface code, we also pretty much know everything. So we do give a lot of freedom on what you can do. You have the four lattice surgery primitives, grow, shrink, merge, split, and we have a bunch of gates that we have pre-defined for you. The auxiliary CNOT, the transversal Hadamard, and you can move the qubits. T-gates will also be ready by the end of the year. We're finishing reviewing that part, and it will soon be there. Now, Loom also has this concept of code factories. So we when we ship Loom, it comes with these 5 codes. Rotated surface code is the most developed one. Educationally speaking, it makes a lot of sense. Then you have the repetition code, which is also a really nice playground where you can build complex stuff. And then you have smaller codes, Steen, Shor, 5-qubit perfect code that you can use to play around with. And note that, as I said, not all these operations here are defined for all qubits, for all mods. You will have some that make sense only in one scenario, not in the other. Now, Entwine, very quickly. When you load when you go to entwine.entropicalabs.io, this is what you see. These are some patches I've drawn, and these are all logical qubits. Two important things to notice: Entwine is free to use, but it's not open source. Now, every time I draw something here, Entwine speaks to Loom, and Loom validates what you're doing. So the scientific backend behind Entwine is entirely open source. The JavaScript front end at the moment is not, mostly because it makes our life easier, sort of just managing that internally rather than opening it up to the community and sort of having a lot of different paths taken and then having to deal with that aspect. But again, it's absolutely free to use. You can just go and check it out after. Controls, as I said, you can create your stabilizer pretty easily, and you can do complex structures with your stabilizers, like rotated surface codes and more. You can copy paste things. So in this case, you draw first logical qubit, and then you can either cut it somewhere else or just copy it elsewhere. Memory experiment. So let's head over to Entwine, and we can have a more live presentation. I think you can see this, the screen, right?
Yes.
Okay, so as I said, it's very easy in general. You would just either drag or drag with shift, and you can draw things. If I do Control or Command Z, I move back. Now I can also use the preset. So if I go here, I already have a surface code built, so I can quickly do it. Or as I was doing for the other one, you can make it much bigger. So memory experiment, the whole point is you just want to create a surface code, and you want to go into lattice surgery mode. I press S. As you see on the right-hand side, Loom code is being generated live. And what I do is a memory experiment. So I instantiate it in 0. I could change the state to 1 or plus or minus 0. And then I create a new frame, pressing E, I hold Z, and I select which is the measurement. So it's very simple. We'll have a more complex case after, but these are basically a set of 3 operations to generate the memory experiment. If I go to the output, I can get the code in different languages. So this is the Steam, Chasm, and ECA, although the ECA is not particularly user-friendly when it comes to this. Now, what I can do after is I can share this tab instead, and basically I can copy the code directly from Entwine and I can run it. So I just need to import a few things from Loom. And this is the code we had before. So you can see, oh wait, let me copy it again. Seems there is something missing there. There we go. I was missing this one, I don't know why. Let me remove this. So it's the same code I copied from the other one. Reset all data qubit, measure block syndrome, measure the logical Z. And I can inspect the ECA. As I said, the ECA at this stage is something that has a relationship between things, but not everything fully worked out. So I have some kind of, you can see this look like the circuit things, and the measurement will have an ID, and this ID of the measurement then is going to be taken back up here, and you have ways of connecting them and ways of making it all work out. And when I look at the interpreted, that's exactly what's happening. So in the interpreted case, the circuits is scheduled, things are moved through, and I start having some more relationship between all the different cycles. Remember here, I just have one single cycle that is showing what you want to do. Here I have 3 cycles because in my memory experiments, I need to perform it more than once to be fault tolerant. And I start having something like the syndromes that I'm extracting, the corrections I may have, the coordinates, space and time where these things happen. So the ECA keeps track of all of these things. It's not supposed to be easy to read this. It's just giving some indications. What do I do with this at the end? Well, you can execute it. So if I take Steam, I just import Steam normally. I do the conversion, so from ECA circuit to Steam converter, and I convert my interpreted ECA into a Steam circuit. And then I can run a simulation. And what I will see here at the end is that my logical outcome is 0. So I started in the logical 0 and I obtained the logical 0. This was a noiseless simulation, but it's nice to see that it makes sense. So what we've done here was a memory experiment. Looking back at Entwine, I can with Q and E, I can move between the things. What happens here is that I create a logical qubit. I keep it alive for 3 cycles. And then I measure its state at the end. That's what a memory experiment looks like. And it's easy to do them in Loom. Next. In this example, I've converted to Steam, but you can convert to more target languages. So on this diagonal line, if you want, you have Steam, which is by far one of the greatest resources when you want to run QEC simulations. I guarantee everyone out there uses Steam. It has some limitations. We'll see in the next slide. That's why we also built our own CliffSim. CliffSim is not for speed, but it allows us to have a few more features that sometimes are useful. Mostly classical control flow. So the ability to put if-else statements directly inside your stabilizer simulator. If I look at the upper part, I have two interesting ones, NVIDIA and PennyLane/Catalyst. Now, both of these frameworks are very developed when it comes to hybrid computations. So it's relatively easy, asterisk, 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 to add decoders that will work in real time in those programs. Now you could ask, why do I need decoders if I'm just doing Clifford simulations? Well, the point is, as soon as you start thinking about T-gates, you're not Clifford anymore. Steam doesn't quite work anymore. So you need to think about alternatives. So these two offer good alternatives for that. Chasm 3.0 and Qiskit, also true for Qiskit. Qiskit has a lot of simulators, so it's very versatile. Many things you can do over there. And finally, Guppy. Guppy is from the Quantinuum stack. It's an extremely interesting piece of software. I always recommend people to have a look at that. We have the code privately. We're just in the process of porting it to the public repository. I think it should be there by the end of the month or early next month. Now, just a bird view of all of this, as I was saying, we have Clifford simulation, classical control flow, that's if-else statements that you can put inside your quantum circuit, non-Clifford simulations, and hybrid compilation. Hybrid compilation being, you take a measurement outcomes and you want to compute the square root of it, for example, and then based on the result, do something. That's something really hard just to do with if-else statements. And this is a little bit the list. So Steam, it's really good, but just a Clifford simulation. CliffSim also gives you a bit more on the classical control flow, very good for debugging and when you're trying some stuff. The NVIDIA Quantum and PennyLane and Qiskit give you everything with asterisks. I think among these, one very interesting aspect is QRAC. I'm sure many of you guys are probably familiar with the tool. It's something that I'm currently testing and experimenting. If you want to help, that's going to be a very, very interesting field. I think trying to see if we can leverage what all the nice things that QRAC can do to do interesting things in the non-Clifford regime. And for the hybrid compilation, if you're not too familiar with it, don't worry too much. I think it will be maybe more relevant in the next years. But fundamentally, it's really the question of like, how will I compile within the same program both the quantum and classical information? Chasm 3.0 again does it, but if I ask you, please implement machine learning classifier algorithm only using if-else statements, good luck. I'm sure it can be done, but it really feels like completely reinventing the wheel, so it's difficult. JAX and PennyLane and Catalyst offer a solution for that. NVIDIA offers some solutions. We'll see how they move forward and where do we go with all of that. Now, adding logical operations. The memory experiment, you create a logical qubit, you set it in the 0 state, and you wait, you start your clock, and you just wait. You see what's going to happen. Maybe you want to do something more interesting, right? Maybe you want to do some gates, some logical gates on top of it. That's what lattice surgeries are about. Now, there are 4 primitives. I'm not going to teach about lattice surgeries today, but I'm just going to give you a glimpse for it. The operations are growing a block. So if you see, we're growing a block here in the first example horizontally. You could also, of course, grow it vertically or on both dimensions at the same time. And you can shrink a block. Very, very interesting thing when it comes to lattice surgery. Remember, in quantum error correction, you have redundancy, right? That's why you still have a single qubit and you can make it bigger, encoding more redundancy in one direction, or smaller. Of course, there is a limit to how small you can make it. There is not such a limit on how big you can make it. But these are very natural ways of deforming your logical qubits. And the next deformations that you can do are, of course, topologically more interesting. I have two logical qubits and I merge it into one. And I have one logical qubit with a split, and I split it into two. Again, from a quantum mechanical perspective, having one qubit and splitting it into two makes no much sense, right? If you think about unitary quantum mechanics, you'd be like, what the hell are you doing right there? But here you're talking about encoded qubits, logical qubits. So effectively, every qubit is around 20 physical qubits, so you have a lot of space. And all you're doing when you do something like a split operation, for example, is you measure a bunch of the qubits in between, and this induces a change into the new 2 qubits that you obtain. If you've ever seen measurement-based quantum computing, this is very similar. If you've seen what psi-quantum does, it's not this, but flavor-wise, it's very similar. It's the whole idea of using measurements to induce transformations elsewhere. The simplest example you probably all have studied at some point is the teleportation protocol. When you do the teleportation gadget between 2 qubits, fundamentally it's very similar to what happens here. Now, let's see how you can do this on Entwine. So we're going to do a logical CNOT between 2 qubits. First thing you will want to do is define 2 qubits. So this is one way you can do it. So just draw your first qubit and then paste it down. The layout is important. If you want to do a logical CNOT in this format, you need to put them on a diagonal with one column in between and one row in between, exactly as you see them here. In the next slide, we're going to run through the thing and you'll see a few. So first, it's going to set the first one in the plus state, grow it, split it, and then you merge the auxiliary qubit and the lower qubit, and you shrink it. Again, we're going to show it again. You grow first, so this creates 2 qubits, and they are entangled, and then I entangle the auxiliary qubit with the lower one. So in some sense, this L shape in steps is transporting information from the very first qubit to the second one via these splits and merges that you do. And this is interesting because if you do work out the math and you check the stabilizers and the logical states, you will see that this exactly implements the CNOT between the upper qubit and the lower qubit. As you see on the right-hand side, all of this is immediately generated, like the Loom code is generated for you. So I can just take this, copy paste it, and bring it to a notebook and analyze it, modify it, execute it, obtain some results. So small caveats here for those that are that have seen through it. You also need to take care of some logical corrections when this happens. When you measure, measurements are very powerful, but they are stochastic in quantum mechanics, and they give corrections. They're all Pauli corrections, stuff you need to take care of. In the case that we give you pre-built, so in our version of the auxiliary CNOT is already built in there, but if you're doing your CNOT this way, you will need to take care of the corrections yourself. But you do have, if you remember from before, logical X, Y, Z, so that is doable. Yeah, so you can stack more examples of this and see where it goes. Now, you can also, if you're familiar with TQEC, visualize the code using these pipe diagrams. Now, what this pipe diagram is really showing is that you have 2 qubits, and then 1 qubit gets created. That's the third column, the one without the bottom part, and then it's transposed to the other one. You can do things more efficiently, of course, than this in general, but it's a nice way to show up the geometric space-time relationship between your qubits. TQEC it's much more advanced, I believe, than Loom, a bit more difficult to use, but is also only for this type of codes. Loom can support any code you want. Of course, the visualization, it's restricted to surface codes. Now, before we bring our own code, I will also show you a small example for the GAZ. So the GIZ, I hope you're familiar with. I forgot to write it, but it's the 000 plus 111. 111, yes, I said it 3 times. So what we will do now, sorry, back to entwine. Up. Yes, back to entwine. Let me reset everything. We're gonna do the GIZ state, but we're gonna prepare it in a pure lattice surgery context. So the general way to do the GIZ state preparation will be doing 2 C knots, but in this case we'll do it a bit differently. So first of all, let me generate a long, maybe too long. One less. There we go. No, one more. Okay. So I want the distance to be exactly 11. I'm not very good at counting. Perfect, 11. So I have my patch, and the size of the patch is, the distance is 11 in this direction. Now, what I do is when you implement a split operation, really what you do, this is equivalent up to some correction to do a C knot between the 2 remaining patches. So if I just want to do a logical gate purely using lattice surgery primitives, I can think about it differently. I don't need to think about the all C knots and all of the structure, but I can just start selecting this into plus, new frame, I can split the first time, new frame, I can split again, and now I have 3 qubits. And by the magic of lattice surgery operations, again, it's very interesting to see this and work this out. But what I have now is a logical GIZ state among these 3 qubits. Now, if you want to verify this, I can wait before. Let me do another frame. I can measure the first one, measure the third one, the second one, and the third one. So if I press Q, I will move back through the list of operations I've done. You see frame 1, frame 2, frame 3. That's pressing E, and Q sends me back. So we start in the plus state. Frame 1 is a split of the alpha frame, and I get 2 more. And these you see the API for split. And then I measure 2 block syndromes. Then the next frame will be the second split. So again, I just keep track of the names. And now I have 3 blocks that I need to stabilize. And finally, I have 3 blocks that I need to measure. Again, I can get my output and I can get the visualization. That's interesting in this case. And I can copy my code. Should be fine this time. And I can go to my GIZ experiment and we can check that everything makes sense. So this is the same one from before. Alpha plus alpha, the first split, 2 measures, third split, second split, sorry, 3 measures and everything. Okay. I interpreted ECA. As always, I convert it to Steam. And then I have a simple function here. Now I'm doing 10 shots. So here I'm using a different function and a different method in Steam. But I do the simulation. And then all I'm doing basically is I am obtaining from here the measurement outcomes for the last 3 items in the Steam simulations, which correspond to the logical measurement, the 3Z measurements that we have selected up here. When I do this, and when I execute it, I will see that my results are true, 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 or false, false, false. Remember, the state was basically 0, 0, 0 plus 1, 1, 1. So it makes sense. I measure in the Z basis. Sometimes, like half the time, I will either get the 3 zeros and half the time I will get the 3 ones, but I will never get cross terms. So indeed, we have prepared a valid GIZ experiment. And note how different it is when you think about lattice surgery operations compared to having to do the C knots between the individual qubits. The footprint of your operation is also very different. One last thing that I just wanted to show. Perhaps I forgot to say, let's look at the chasm circuit. This is the chasm circuit, just to do this experiment. you see how long it is. We're talking about over almost 2,000 lines of code just to run this experiment. That's why I say thinking about the circuits, it's not like circuits maybe shouldn't be the first thing you concern yourself with, but you should have higher abstractions that make your life easier. Okay. Finally, the last example, I think will take around 10 minutes, and then there's going to be 10 minutes for questions. And otherwise, you get the time to have a coffee before the next presentation. So again, a live session. What we're going to do now is we're going to implement a code from scratch in Loom. We're not going to go through all of the details. This example is actually worked out in the documentation. But basically, we're going to do this color code here to the right. Now, what you need to do when you do this kind of examples is first choose a code, study it, define the lattice. Now, we're not 100% set on this idea of lattice. It's useful for certain things. It's a bit more cumbersome from others. Maybe eventually we'll change it, but at the moment, that's what it is. So it's basically like just geometry where you're going to put all the labels for your qubits. You define your stabilizers. You will match stabilizers and syndrome extraction circuits. You define your blocks, operations, and you interpret the circuit. So we can go and see this example. Now, this is taken from the documentation, so there is a lot of wording, a lot of code. You don't need to read. Just follow me so you get the general understanding. We're creating a lattice here, and it looks a little bit scary. Once you've done it once, it's fixed. Of course, this is going to be an hexagonal lattice, so there's a little bit of math and geometry to make it work. But you basically kind of deciding where the X and Z ancillas and data qubits and ancilla qubits will be placed. You need to have some coordinates to do this, and then you can plot it. So basically what you've done above, and you have some examples that help you to build this, is you've generated this lattice with the correct, actually rather than correct, it's more like with a system of labels that is meaningful to what you want to do. Doesn't need to be unique. People can choose different conventions, but the idea is to basically give you the freedom to define a geometric space and a set of labels that then will make your life easier afterwards. Now we can start saying, okay, we just want to define our logical qubits, so we only care about this triangle now. So let's forget about the other ones. Let's restrict ourselves to this. Next, you need to create your stabilizers. Again, logical operators are relatively easy because we want to put them all at the very bottom. If you remember, the picture before is at the bottom of the triangle, but then you need to figure out how to put all of your stabilizers. There is some helper function to do this, and then you just basically create your stabilizer lists. And these are composed by the terms with 4 X's or 4 Z's, or 6 X's, 6 Z's. Again, the reason why I'm showing you this is there is no free lunch, of course. But once a code has been added to the Loom code factories, then anybody can use it. So there is a sense of repeatability. You could do this with Steam, of course. The problem, if you believe is a problem, it may also not be a problem, of course, is that everyone will need to create their own ways of generating these stabilizers and their own way to do it, which involves loops, custom functions, and whatnot. I think this is an interesting way of doing it. Step 4, the syndrome extraction circuit. So ECA, scaffolding, blueprints, you start by having these definitions. Now you want to say, okay, how do I measure this? Can I just write once the circuit for, let's do the 4-axis because it appears more. Can I just write it once and make sure that every time I say measure a 4x type stabilizer, I don't need to see the indices. I don't need to think about the indices. I don't need to think about the circuits, but I know that all the gates are properly matched. Yes, you can. So the idea is that you have a list of syndrome circuits. And the way that this works is that you have, in general, a standard way to define your syndrome circuits. Standard way is just look at the stabilizer. Is it an X? Is it a Z? There is a corresponding block in the circuit. So that's what we're using here. You could also, of course, define an entirely different circuit for distraction, and we have tools to validate that. That's a bit of a more complex feature. I'm not going to talk about it today. Okay, we have the stabilizers, we have the circuits. Let's bring them together. So we do need to explicitly write the map, source of pain and potentially errors. But once you've done it, you've done it. And now you have a map between the stabilizers and the circuits, which means that as you go through the workflow, you can always match the two. And that's going to be extremely useful because then you need to do less work. Okay, we're ready to create our block. The block, as we saw in the example of the repetition code, is going to be a label. A lot of fantasy, we call it Q1. You have your set of stabilizers, you have your syndrome circuits, and you have the map between the two, and you have the logical operators. These are the bare minimum objects you need to define a logical qubits. Next, we do the logical circuit. Again, for free, you can directly get the code elements, sorry, the operations that belong to any code. So this you can just import, and they are automatically, they should automatically work. Of course, bounties for bugs will be put eventually, and it's great if you find an issue with this, but it should just work. Which means that I can just define the operations. You don't need to rewrite this once because it's a planar code, everything should work fine. And now you're ready to set your ECA. So you have your lattice, you have your blocks, your logical qubit, and you have the operations. So we have just done a little memory experiment. Did I run the previous ones? Yes. And then again, we can interpret the circuit. We can plot it. So of course, this plot now doesn't have all the colors, but you can see that the stabilizers are the right ones, the 6 and the 4 ones in the right places. And down here, you have your logical qubits. Yes, your final circuit contains some ticks and informations. And then what I just wanted to show you is that you can also use ClipSim to look at it. Now, ClipSim, it's more experimental in many sense. So what you get here at the end, after I've done the engine, ClipSim engine run, sorry, after I've invoked the ClipSim engine run method, I get a list of all the stabilizers that belong to the last set. Now, this is not super intuitive to read, but you want really to see, figure out that you're still in, that this is compatible with this. That's something we still need to add. We are in the moment refactoring all the executors, so all of the backends need to be a bit made more consistent and refactor. So that's coming soon. But I just wanted to show you can do other things apart from Steam without having to load anything in Kudaku or something a bit more complex to explain. Okay, back to the slides, and we're almost over. I'll just give you and leave you with some summary and conclusions. So it's going to be like a little video playing on the background just because you haven't seen enough videos during this presentation. Today's capabilities. Entwine is a web-based GUI. It's free to use. You can use it as much as you want it. It's great for learning and building lattice surgery operations. Of course, if you're dealing with 100 logical qubits, you want to do that programmatically. You don't want to draw all of them. But if you're dealing with like 20 of them, probably Entwine can still hit that sweet spot and make your life easier. We'll be adding more and more documentation about this over time, and it's going to be easier and easier for people to learn about lattice surgery, and that's what we hope to achieve with this. Loom, on the other hand, is a very general tool that allows you to build any quantum error correction code, which is based on stabilizers. So Limit is a little bit the sky. There's a huge library of quantum error correction codes. Work needs to be done. You don't get things for free, but I assure you once you have done it, so if you've done it once or if somebody has done it, then it's easy to reuse it for everyone, which I think is a great point. Now, what can you do with all of this? You can benchmark and compare QEC codes. So you can do the memory experiments and threshold experiments. You just need to basically load them up in Steam and follow your regular way of doing things over there, or add utilities to Loom. We do it internally, but we're not forcing people to think how we think about this. You can design quantum error correction codes from scratch. So we have internally worked BB codes, HGP codes, basically families of QLDPC codes. So this is doable. You can just go ahead and do it. You can think about real-time decoders. That's something that I've been working a lot during the last year, but you can do real-time decoding through PennyLane and Kudaku, of course. It's extremely interesting. It's a big field. I encourage everybody to look into this. And of course, you will be able to move quite easily outside of Steam-based simulations. Where to get started? We have two main websites. One is Loom Design website. It's the one on the left. It's more high level. Here you will find sort of more like tutorials. You don't really want to know how the lattice works, or you don't care too much about how the interpretation step of the ECA works and so on and so forth. You just want to use the tool. That's the right place for you. The API reference is the lower level stuff. It's the place where you're going to go if exactly you want to figure out what's the signature of a function, why have we done things in a certain way, and it's a bit more low level, more aimed at programmers. The last thing I would say is we have just released the tool, basically open source at the beginning of November, end of October, beginning of November. The official launch for the tool will be this Friday. So we'll start making this coming Friday. We'll start making a bit more noise about it. Expect bugs, but it's an exciting time to be working on quantum error correction. We are at the beginning. If you believe what I said about from 2025 to 2030, there's going to be a hunger for quantum error correction. And if you see the lineup for today, I think Riverlane is speaking right after me, and they're also going to say very similar things. And I think you have a few more presentations. I think you had some good stuff from Alice and Bob as well. If you really believe that the world will be interested in quantum error correction, I think it's a great time to get into it. I believe Loom, being completely open source, makes it very transparent, and it can be a great place to get started and learn about quantum error correction. It's a new piece of software. Expect bugs, but if you have ideas, or if you find bugs, or if you want to contribute, we are extremely open at that, and we'll need help if we want to make this successful. So this concludes my presentation. Thank you so much for your attention. If you have questions, I'm very happy to answer them. If it's early in the morning and things are quiet, I'm also happy to give you like a few minutes before Riverlane starts.
So thank you, Leo. So I have a few questions. First of all, is NY?
Entwine.
Yeah, NY work for both Windows and Linux systems?
Yes, it's a web-based. So you just go on the website, and it should run on any browser. Now, I don't think I should say this. Sorry, I think it should work on Chrome. Then if you really have problems with other browsers, let me know, and somebody in Entropica will start crying. And
So thank you. Any question from audience? Yes, please.
Yes. So for Entwine is clearly designed specifically for surface codes, but there are some other LDPC codes that have at least also some geometrical language to them. They're encoded in graphs or square context.
Yes.
Do you think Entwine has the potential to extend to cover such codes as well?
Yes, potentially, yes. That's something we've been tinkering a little bit with. The thing that wasn't, so I got very excited at first, but then like the people that were working with it just were telling me like, but I can just write the graph and that's it. Like they saw less of a good use case for that. But yes, I agree. There is a way in which you can think about graphs and then convert them into quantum error correction codes. It could be useful, and it may be useful to do that more graphically. I think one of the main problems is that a lot of the people working in this field are mathematicians. Like they come a bit from that side, and you know they don't like to visualize things. They just like to write expressions nobody understands. I'm a physicist at heart, so you know it's like, yeah. Sorry, I think I answered your question.
Any question for Riverland? Yes.
Was waiting for other people. Can you hear me?
Yes.
So one question about the GHZ state preparation that you demonstration you did. Is it a fundamental limitation that the split operations are done in different steps, or
Yes.
Okay.
So for entwine, so it's not a theoretical issue. Like I think you can do them at the same time step. When you draw your graphs on entwine, the way it was developed, it gave issue on the compilation part, so on the translating part. But in general, that's not a strong requirement. Yes, I forgot to say. In general, we suggest people just to do one operation in each frame. That's why we call this design, right? To some extent, it's great for designing, and then probably you're gonna take the code and still make a few changes so that you tweak it for what you want to do. Kind of takes you closer to where you want to be. Yeah.
Okay. Makes sense. Thanks.
Any more question? The question from online. So I think it's good. Leo will stay with us for the hackathon, so don't worry. We will have a lot of time to practice about the end-to-end system. So thank you, Leo, for this very beautiful presentation. And so right now, we move forward for the next talk by Jesus Sanchez Herrero. Directly. So he will talk about the material revolution, carbon nanotubes as the road to FDQC. This is an R&D engineer and business developer working at the intersection of quantum computing, nano devices, and strategic industry collaboration. He's a part of the business development team at C12, where it focuses on the client projects, partnerships for one of the Europe's leading startups developing scalable carbon-based quantum processors. This is coming. Sorry, we will set up a little bit for the slide.
Just 1 minute.
We have time, no worry.
Oh, wow.
Google.
J'ai envoyé les liens à Poulain parce que sinon
À Poulain?
il faut l'accès. Il donne l'accès pour le temps. in
Right. Yes. Just share the screen. It's like
Normal.
là, il faut juste tu bouges ici. Allez, exactement, voilà.
Okay, so sorry for this small technical issue. My name is Jesus. Actually, this is probably going to be the less scientific approach today. I'm coming from the business team at C12, and I'm focusing on the projects with the clients, but also the scientific partnerships that allow us to build the whole projects for our company. So the central topic that I wanted to understand today is how C12 is innovating through material science. Our approach to fault-tolerant quantum computing goes through the improvement of our material, that is the material that is hosting the qubit, and our vision is really related to the improvement in fabrication, etc. So this is a central idea to what we do. And who we are, and also the use of carbon nanotubes. I was having a look, and I think we are the only company in the world that is using this material platform to host qubits. So it's quite interesting, but it's also challenging because we don't really have other benchmark against. So I was expecting to have a bigger audience, but what I wanted to ask you before, maybe I will ask you because you smiled. What you're expecting for the presentation today, and what you want to learn, what you're expecting to learn from the presentation, just to have an idea.
Technology C12 is using for their hardware, maybe?
Yeah.
Other than the hardware, if they're working on anything else, like, I don't know, correction algorithms or something else.
Cool.
Or what products they're offering.
Exactly. Yeah. So the topic of today was the hardware. So that's a good point. You will see at the don't worry that I'm coming from the business side. You will see on the last slide that we have, like, you can still ask questions if you're interested, and they will be answered. Also, yeah.
I'm interested in the difference between C12 approach and other approaches, such as we are way better on that, but we are a little bit less efficient on that.
Of course, yeah. Yeah, that's also very interesting. I was gonna say unfortunately, but it's not unfortunately. I joined the company almost 2 months ago. But as I said, any questions that you have will be answered today or on a different day. And thank you both for your questions. So I will start with, if you're interested about the company, I will start by sharing briefly the history of the startup. We are based in the center of Paris. It's the only one that is based near the Luxembourg Gardens. So a very cool place to go to work every day. Our vision, so you were asking about the hardware and how we use the nanotubes to host the qubits. Something that is really cool, and this is not easy for the center of Paris, is that we have our own foundry. So we have an in-house nanofab that I will show you on the slides later, but we were able to do everything on our own, from the really low level of fabrication to the low level control stack, part of the stack. And then I also want to talk to you about the emulator that we are developing at C12. This is a central part of our value proposition, since it's a platform that is uploaded on the cloud access that is not just for us for internal research. Actually, clients are using it already. So it's a very, very cool thing that we have developed at C12. And this is maybe linked to what Adrian was asking, or what makes us different. Callisto is one of the main things. Also, since I'm coming from the business team, I will talk just a bit about the from my team. So first of all, we were founded 5 years ago. It's a spin-off from the École Normale Supérieure, Ulm, in the center of Paris. Right now, we have 50 million in total funding, equity and public. This is coming from the business side. We are 65 employees now. C12 is growing a lot. And as you will see at the end, we are hiring people. So if you're interested, don't hesitate to scan the QR code. It is a very international company. English is the working language of the company, and it's not just promises. We have actually 8 patents and multiple world first results in articles published in Nature and other scientific peer-reviewed journals. I don't want to bother too much with the company structure, but I think it's interesting to see that both of the founders, who are twin brothers, by the way, they come from a very technical background. Even the CEO, they both did Polytechnique, and then they have been working on quantum research for a long time before they decided to launch C12. And this is just a way of saying that the company really focuses on scientific rigor. And in quantum, sometimes it's good to have some rigor because there's so much companies trying to use the word for just trying to capitalize on it, that this is very relevant. We also count with scientific advisors. Most of them are in the École Normale Supérieure. This is also why we are based in the 5th arrondissement, but also Institut Néel in Grenoble. And just before I go into C12, just wanted to share why we are focusing on fault tolerance and quantum computing in general. So if you are at this event, probably you don't need this slide, but one of the promises for quantum computing is that it will allow us to solve problems that are intractable classically, and this is going to affect, this is promised to affect many industries across the world. Again, the different problems we work with at C12 are simulation problems. I will show you a use case where we worked on chemical reactions. We are also, I would say now more than before, we're focusing more on optimization for the financial sector. And we might explore quantum machine learning also in the near future. So these are some of the problems that we are working every day with. But of course, to reach the full potential, quantum computers need more qubits. So that's where the central focus of the company is at. Again, to give you a reason why the company focuses on fault tolerance, and quoting John Preskill, who's well known in this area, Like looking from the business side, there are companies who prefer to capitalize on NISC era solutions, but we prefer to focus on fault tolerant because we really believe that the commercial value that this approach has is bigger than the NISC, and also, according to what he said, there are no theoretical arguments indicating that commercial viable applications will be found in the NISC era. So this is one of the reasons, commercial reasons, why we focus on that. And yeah, so if just to name drop some big companies, so Google, Microsoft, and Amazon, they could have focused on NISC era, but they decided to focus on fault-tolerant quantum computing. And as I will show you now, there is this graph where you try to go from the NISC era to fault-tolerant quantum computing to obtain as much revenue as possible. There are some companies, and this is respectable, some companies prefer to capitalize on the solutions they can provide here, while others really prefer to focus their efforts, even if they don't bring as much revenue now. But they prefer to focus their roadmap and structural efforts of the company in this direction. And this, for a company, I know it sounds like blah, 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 but for a company, it's not an easy decision because you need to, of course, it's not a public research lab. You need finance, a constant, to sustain the company. So, and probably I'll be more comfortable talking about what I do at C12 every day. I'm not working on theory, I'm not working on fabrication, but from the business development team, it's actually very interesting also what we do, because the focus of the work, as I said, is on clients, but also scientific partnerships. So I help the company identify potential collaborators we might work with. Of course, many ideas come from the theory teams because they know better than anyone the problems they have. But I help to identify collaborators, to manage the, maybe you're not used to this kind of things, but this is a Gantt chart. So it allows you to manage the different deliverables of in project management, and that's basically my everyday. I also help to deliver these collaborative projects we do at C12, and also identify European calls we can apply for, and of course, pre-sales. So that's where networking comes in, and LinkedIn and all these things. So why are we doing this? Of course, every company in quantum is collaborating. Nowadays, it's not that we are worse than anyone. So the focus of C12, maybe this is just answering your question. We address really the low-level physics of the quantum hardware, and also a bit of the low-level control software part of the stack. So for the other, for different activity, for different tasks, we need to partner with other people. So we are partnering for error correction, even if we also do it in-house. We are partnering for algorithm development, and I will show you a use case later. And also we are partnering, of course, we have as clients companies, and the companies, they define the use case, and we work with them. And an example of something we did was with Thales. Do you remember Callisto? I talked at the beginning. It's the emulator we have. So actually, it was not developed to be an annealer, but our software team create new specifications and features to make it work as an annealer. And thanks to this, we were able to run one of D-Wave's algorithms. Yeah.
Can you quickly explain what annealing means?
Yeah, so, well, maybe I'm not the best to explain this, but what I understand is that in quantum computing, you have digital gate-based computing, and you have also analog. And if I'm not wrong, the only analog approach I know is annealing, right? So it's got one kind of analog quantum computing.
Yes, we have.
Do we have a discussion on annealing in the festival, or someone's going to talk about it?
We don't No.
There are famous companies. I can tell you from the company side, there are famous companies doing annealing. It's the Wave in Australia, Pascal. Well, Pascal is doing analog, but I don't know if annealing, and Kilimanjaro in Spain. Just because I'm Spanish. Yeah, I know Kilimanjaro is doing it. But that's a very good question. So for us, it meant that we had to change the way the emulator was built from the very basis and add new features. But of course, this is all because we are working on product development. So this is always interesting. And the good point here, it was the speed up that we achieved. So I just mentioned a very general number there. But actually, when we compare our results on Callisto to what G-Wave did on their own computer, we had better results. Like the speed up of the execution was improved by 10. So these are results that is very promising for us in optimization, and it encourages us to continue working in this area. The use case, let me take the time. So the use case that I'll be showing you now, and this is another example of collaboration that we have, is it's chemistry simulations. This is how you fit it in the quantum computing. Many industries depend on simulating chemical reactions. So from the industrial side, this is very interesting. I actually come from a background in nanofabrication, as they know. So I have also been working with atomic layer deposition. And this is one technique that, I mean, the company contacted us because they wanted to see, they are testing new precursors, and they wanted to run simulations to find the best candidates for the chemical reaction. I don't know if you guys are familiar with atomic layer deposition. So basically, and again, maybe, I know you guys were working in theory, so maybe not so much. So atomic layer deposition, it's a fabrication technique in which you have, of course, a chemical reaction in the process. So this is where the quantum computing comes in. You are trying to simulate, you are taking different precursors, and you are trying to simulate which ones can get the best solutions. Nowadays, this is mostly done by DFT. That's the functional theory. So the idea was to benchmark against DFT. This is, I know you could tell more about that. So what happens with these kind of problems, chemical reactions, is that they have a huge number of variables, making the problem sometimes intractable. And okay, for the company, and I will give you the name of the company now, being able to simulate this reaction is really important because it saves them time and also, of course, experimental resources. But this is just why simulations are good in general, right? So these are the companies we collaborated with. The industrial sponsor that gave us the use case was Air Liquide, which is well known in France and Europe. I was saying before, we need to collaborate for sometimes algorithm development. So this is where they come in the picture. We had some, we defined the project in a way that the algorithms we were gonna try were variable quantum eigensolvers or eigenvectors with a classical optimization loop at the end. And the idea was to have, okay, so Air Liquide provides the industrial case. Quantinuum comes with the expertise in developing binding energy algorithms. Then there is C12, and we provide our emulator, which is, as I said, mimicking what the hardware is going to do in the future. So just to make this very clear, we are a hardware company. Callisto is just there to mimic what the computer will do, but you are seeing that it already has industrial value. So this is something that, for example, makes the approach of C12 different. And this is what I was saying. So we obtain a higher accuracy than classical DFT. And there is a paper, if you want to check it later, where we show the results. This was phase 1 of the project. They were so happy with us and the consortium in general that yesterday, from the project management side, we launched the kickoff of phase 2. Yes?
You said that have high accuracy than classical DFT, in which What you are trying to measure?
Yeah, that's a good question. So for the I don't you're asking for the physical parameters.
Yeah,
that-
exactly. Yeah.
Yeah, I'm actually I've read the paper, but I don't remember now. But this is why I also cited. So you know, but I didn't have time to, because I could say something about the energy, but I don't remember exactly. I don't know if it was the binding energy. Maybe it was the binding energy, but I don't remember. But yeah, again, from the business side, for what is important is to say, hey, we are better. No, but also you have the paper to check. Yeah, so again, we kicked off the phase 2. This time we are gonna try a different kind of algorithms on Callisto. So this is from the very well-known work of Olivier Srati. This is just to show you where we fit into the huge constellation of different approaches to quantum computing. I think you were asking about annealing before. You can see here there are mainly 3 companies in Japan, Spain, and Australia doing annealing. You know about Pascal, they are doing cold atoms. There's also, I don't know, Candela. So we are fitting, or Alice Bob, we are fitting here. So we are, I mean, they decided to fit us in the silicon column, even if we are in a special part where we are doing nanotubes. And this is because we are the only one in the world, so we don't have a category for us. It's just we are standing alone in the silicon column, even if we are not doing silicon. Yeah, yeah, exactly. Also, when I was looking, it's like, no, we are not silicon, but it's just because we are doing electron spin. So, and we had to fit somewhere. But yeah, the important thing is that we are doing spin qubits. So this is the spin cube. It's a very scientifically accurate representation of the electron inside the nanotube. Now, just kidding. This is just a cool way to show that we are using the spin of the electron is trapped in a double quantum well, and then the structure itself of the nanotube, it allows us to reduce the amount of noise as much as possible. Again, a very fancy picture of the central part of the QPU. You can see here we have electrical contacts, and also we have gate electrodes. And this is, as I said, the central part of our efforts are in improving this part of the workflow. So you might be wondering what are the different parts of the setup for. We create a double quantum dot using the gates that we fabricate using superconductor materials. And the idea is also to execute the gates on the qubit using the electrodes through electromagnetic pulses. So why? Yeah.
One question. So you create the qubit, you put electron inside of nanotube, and how they connect to each other. For example, if you want to create 2 qubits, you have to put 2 electrons, right?
I hope I will answer that question later. Okay. I hope I'll be able to answer. Yeah. So basically, what I want to say here is that why are we doing spin? Because there are other platforms, and we don't really know what's gonna give the best solution. Maybe you think, no, actually, trapped ions are better, superconductors are better. Actually, we don't know. So there are these technologies, according to the report, they are more mature, but they also have some bottlenecks in terms of speed and connectivity. I'm not trying to say that spin is the best. We really don't know, but we believe so in our roadmap. And the problem is that also it's more on a experimental, it's less mature, it's more an experimental stage compared to other platforms. This is one of the things that we get sometimes is like, you guys have some, we started later than other companies as well. And we are very scientific yet. Most of our teams are PhDs, researchers. And one of the reasons is that the technology itself is less developed. But this is very general in the world. So I don't I don't want to say anything stupid here. I just want to say that, of course, we know that errors are the main bottleneck to scale fault tolerance nowadays. So what I really wanted to say is that some important value figures we have achieved at C12 are in terms of coherent times. And again, these values are very specific to the platform we use. So maybe I didn't bring anything to benchmark against, but this is the values we obtained for our coherence times for the bit flip and phase flip. It was world record. And as I will explain later, answering your question, the way we connect or entangle the qubits is very different compared to other spin companies. So yeah, this is of course encouraging us to follow our roadmap and one day being able to achieve microseconds, milliseconds. Yeah.
To put these numbers in perspective, how fast are the gates, if you can say it, and if you know about it?
That's a good question. Actually, these kind of questions, what I wanted to say is that if you can write them down, I will say it at the end, but it's also for me to learn, so I can ask them to the teams and also answer to you. So I will keep the contacts. So yeah, right. Also, yeah, I mean, like showing numbers like this in the middle of this record was achieved it was 2 orders of magnitude larger than the previously known, but it was in a very similar platform. So but again, good question, thank you. So this is another question. The Proxima program is also one of the things that makes C12 a little bit. I was gonna say well known, but anyway, sometimes we refer to the 5 well known, or I don't like the word top. So it's like 5 companies in France that are making some advances towards fault tolerance. Sometimes we explain this through the Proxima program. And again, guys, I know this is not about physics, but I think it's really cool because the Proxima program was a program launched by the French army, the DGA, in which only 5 hardware providers were selected to compete between each other and deliver a fault-tolerant quantum computing to the army in 2030 at the beginning. So you see, it's very ambitious goals to provide 2 prototypes with 128 logical qubits and 2048 logical qubits by 35.
How many qubits do you have to the physical qubit do C12 have actually today?
Yeah, I will also yeah. Actually, what I was thinking, if you have questions at the end, also I can. Okay. But no worries. So the Proxima program, as you say, is very ambitious, but it was also kind of a selection of the 5 companies that are doing the most improvements in France. First of all, and this is, I guess, is a source of pride for the people who live in France, but I believe it's one of the best countries, one of the few countries in the world which has a solid foundation in the research, but also the industrial capability to one day get in there to fault tolerance. And also these programs like Proxima, which were actually inspired by the Enigma, the program that decoded Enigma. This is a source of inspiration for the Mr. These kind of programs, they really help France develop the race towards there. Yeah. So now this is more of the So now I'm going to talk about the errors from the material science point of view. Again, other companies might focus their efforts on the error correction or other parts of the of the workflow, but we are really, and I know I've said it before, but like our main efforts are really in improving the material and the fabrication steps, because as you will see, this is going to have an effect in the of course in the error correction. There will be less error to correct, basically, roughly. So I'm getting to the to the qubit part. We are using the carbon nanotubes as the building blocks of our QPU. And these are some of the reasons why we believe in this approach. The noise coming from the nuclear spin is very reduced in our platform. Also, we have specific control of different modes, and the nanotube provides a protection against the charge noise. So this is not some reasons from the material side to use it. So again, as I explained before, by mounting the carbon nanotube on this setup, we are able to manipulate the single electron. Sorry, within a within a double quantum dot, and we use a local magnetic field to entangle the electronic spin with a charge dipole in this double quantum dot. And then we address the spin qubits via microwave pulses. So this is the heart of our technology. This is from a paper we published. You can also see how the setup looks on a real photograph, a real image. Yeah. So basically, and again, this is not something I'm working on a daily basis, but what I wanted to say, and this is more scientific, is that the way we control the spin, it's really ingenious. So we couple it to we control the spin through the charge, and we are able to do this because we have we are able to create spin charge coupling. So I don't know if you guys come from a physics background or material science, but really what we do is that we are coupling. Okay, so usually what we would like to do is to control the spin with a magnetic field, for example, because the spins are what was the word I was trying to, sensitive to magnetic fields. But what we want to do is to control the spin with an electrical field. In order to do so, we couple the spin with the charge, so we can use the electrical field to control the spin. This is just a way of saying we can have faster control if we do this really complicated quantum stuff. So really, this enables resonate. I mean, this what it allows us to have in the end is faster control, faster control of the spin, and also, and this is answer your question, Vin. We are able to entangle the qubits, and we do it in a different way. We don't do other spin platforms use electron shuttling or other approaches to couple spins, but we are using a resonator as a quantum bus to perform the 2 qubit gate operations. So I will try to explain it later because it's quite difficult. I mean, it's quite technical. But now I want to focus on this part of the workflow. So we are basically we are using the gate electrodes that we fabricate using superconductors here. We use these electrodes to manipulate the electron in the double quantum dot. So basically, what this means is that we are changing the values for the voltage here, and we are measuring and characterizing. So I don't know if you can already imagine, but this is very tedious. You need people who have, first of all, not like just anyone, like people with a very solid training in quantum physics and constantly changing the values for the voltages and seeing the results. So I don't know if you see where I'm trying to get to, but this is a perfect place to input some, trying to get some automation workflow that can help us. So how are we doing this at C12? So we have dedicated experts that are basically using machine learning, classical machine learning tools for the electrostatic tuning, and basically the formation of the double quantum dot. I will not go into the details, but basically the way they do it is they have some they input some data to the machine learning models of the continuous wave spectroscopy of the interdot transition. It's just part of the process. So basically, this is very small, but this is the setup I showed you before, and these are the values for the voltages that change. We input this into a computer vision workflow, and then the idea is that it automatically updates the gate voltages, and we can find the optimal double quantum dot. So we have, again, dedicated expert in the company that can explain it way better than I do. But something the idea to bring this slide is that we are preparing an activity with students in this area. I think it's really cool because it involves machine learning and quantum physics. Yeah, we don't have much time, but I will give you a hint of the resonator. And again, I want to answer your question about how we couple qubits together. So we are using a microwave cavity or superconducting resonator to couple the spin. So I don't know I know you're not coming from this background, but I will explain it the way I understand, which is not very. So you want to achieve spin coupling, okay? Usually, what you're trying to do is to shuttle in the electrons so that they are physically close to each other, because we're trying to couple the spin of an electron with the other. And this is how other companies are doing it. We have a completely different approach. We have an intermediate step. So imagine there's a spin, there's another spin. We want to couple this to the intermediate step. So, and also this spin is coupled to the intermediate step, which is the resonator, and a way that the information can travel. And in the end, both spins they can transmit information between each other. So this was a very hand-wave explanation, but from the science point of view, it's a challenge, but we have very nice results. So I was thinking of going into more details, but I think it's okay. What this allows us is to have a lower crosstalk, because the electrons don't have to be close to each other in space. And maybe this word is more interesting from a quantum information perspective. Our platform will allow us to have high connectivity. So this basically allows for faster and simpler quantum code. This is one of the places where you can see the material science and quantum information overlapping. Well, if you bought the idea that the resonator is super cool and it allows us to have higher connectivity, then great, because now I'm gonna sell it to you. No, this is the diagram of how it's actually built on the chip. But again, I'm not going into details. Just the qubit sides are connected to the quantum bus, and also we place the gate electrodes on so that they are connected to the rest of the setup. Yeah.
I have a question. Can you go back to the last slide?
This one.
You said here like you are trying to couple the spins of the electrons, but I think they are coupled to a path, no?
To a path?
Yes. External environment.
Oh yeah, that's one of the sources of error that we don't want. So the idea is that since we are using this ultra pure carbon nanotube, this platform allows us to have less sources of error coming from the environment. You're talking about, for example, the nuclear spin or charge noise, these kind of things. Yeah, it's what I was trying to say is that the nanotube structure itself and the way we build it allows to have to reduce these values as much as possible. So again, Let me see if I can answer you with the next slides, and otherwise you can always write the question. So for those of you who come from a nanofabrication background, I think you will find this cool. There is a dedicated team working on the nano assembly process. So basically, it's how we put the nanotubes on top of the electrodes suspended on the gates. Of course, well, we don't buy the nanotubes. We grow them ourselves because we need to be really precise in the nanotubes we are using. So for that reason, we also characterize them and select. So only the best nanotubes can go, and this is related to the noise, like charge noise and other kinds of noise. We really need to have a specific type of nanotube. We cannot have any, and so this is why our teams are working on the characterization and selection. And actually, most of the patents are on the how we integrate, how we do the circuit integration. This is a proprietary technology that we are really proud of since 12. So we believe these approaches will allow us to be really scalable because the nanotubes are really small, so we can integrate many of them together, having smaller devices, and also the qubit density will improve thanks to these, the connectivity thanks to the resonator, and also the short amount of noise coming from the ultra pure platform. Yeah, this is what I was trying to say. So basically, we are aiming for high fidelity, high connectivity, and scalable fabrication. And through these 3 pillars, we really believe to get fault tolerance. For those of you who come from a more technical background, and again, if you have questions at the end, they would appreciate it, because I really want to learn more about quantum information and computing. So our native gate, because of the architecture we have, is an ISWAP, but we can also handle CNOS gates with promising results. Also, one of the ways we deal with crosstalk is we have the ability to switch from active mode, which is what we call when we couple the qubits to the resonator, we call this active mode, and then memory mode when it's not coupled. I'm not going into the physics, but the idea is that we get closer to spin-spin coupling, and again, through iteration and improvement of fabrication, we are also exploring other resonators, etc. So yeah, there are certain points I really insist on because they are really important for us. Yeah, this is just another review of the same thing. So the foundry, if there's anyone connected from nanoscience, oh, I didn't want to do that. Why is it? Yeah, anyway. Oh no, it's because it's a PDF. Yeah, I had an animation. Okay. Can I go back? But it's okay. It just covers the numbers, but I can. I will read them.
You join a team from your PC. To be better.
Yeah, it would be better, but no, but I won't have time to. Well, it's alright. Just I was just want to show the numbers so far.
Yeah.
It's okay, and just some numbers. Cool. I can talk about this then. So yeah, so this is some pictures of our fab. Then I will also show you a video. But basically, all these are the machines that our technical teams are using in the center of Paris. We have space for up to 7 cryostats, and just a lot of space also for the lithography and other parts of the workflow. I will try to show you now. Yeah. Great, thank you. I mean, it's the same, just so what's wrong. Yeah. Basically, there's a lot of space. So it's 900 meters squares in Paris, to 200 square meters of clean rooms and space for up to 7 cryostats. So far, we have 4. And also for the growth and characterization teams. And what is important for us here is to have all the steps of the workflow in-house, so we don't have to depend on other players. Right. So the structure of the teams in the company is also a way of answering questions about the hardware. We have people who are experts about carbon nanotube growth. We have experts on characterization, on microwave or radio frequency design. And in the end, all the teams work together. They have a constant input and output of data that allows us to provide the best results. We also have a really strong theory team coming from École Supérieure and measurement teams. Again, for those of you who know some of the setups, and this is interesting because we are hiring. So if someone has expertise in some of these techniques, for example, electron beam lithography, scanning electron microscopy, this is some of the techniques we use at C12, and that we might hire for in the future, or maybe today. We get our chips from COLT. This is one of the few dependencies we have on the fabrication workflow. And we also collaborate with l'Institut Jean Lamour in Nancy. So how do we fabricate our nanotubes? We use carbon chemical vapor deposition, So through a process of pyrolysis at 1000 degrees, we inject some methane gas into the setup, and the chemical reaction, and we grow the nanotubes on a cantilever through this chemical process. We do characterization of the nanotubes by using different spectroscopies, very well known in the field, so Riley, Raman, to gather some more data about our nanotubes. Let me see if I can. Oh, this is good that I use my computer. So yeah, this is just a very easy animation of the stapling part. Although this was at the beginning, we have patented a different system that allows us to be more efficient. And it's not. Oh, yeah. We are also working on our workflow in the calibration part of the qubit and control. So all of you that have a background in this area, it's also very welcome. I will not have much time, but I will try to. Can I open a YouTube? But this is not allowed.
Yes. If you have Wi-Fi.
Yeah, I do. I will try at the end. It was just to show the foundry. So we have some images on the how it looks from the inside. But you can also go on the internet. It's just up C12 Foundry and you find it. So again, you were asking about the main sources of decoherence and error. There are several sources. We can identify all of these. Some of them can be engineered. Others really depend on the material. So we are trying to focus this on to work on all of them. We have already achieved world records in all these identified decoherent channels. So we can compare to what are the best we obtain, for example, in terms of magnetic perturbations, these values also for electrostatic and mechanical. I'm sorry that I have to rush a bit, but then also, as you know, one of a cool way to see 1 qubit operations is using the block sphere. So the way we do the way we apply the gate is via microwave pulse, and this is another animation to show in a very product level way how we do it. Are we able to do 2 qubit gates? That's a very good question. Actually, yes, we have already results and these fields, and again, this is by using the microwave resonator. So we can couple 2 qubits through this resonator, and it allows us to be able to connect, as far as I know, 2 qubits together, maybe even more, but it's something I'm thinking about, but it's at least 2 qubits together, and also doing A-swap gates. I showed this before. Basically, there are no theoretical limitations to achieve high values of fidelity. The achieving high fidelity and the high connectivity I talked about will have a substantial payoff or improvement for the quantum error correction side. So for people who are working in quantum error correction, you guys really care about the material as well. So the result for us at TC12 is that we're building a quantum processor, a QPU that has no major roadblock. So this means that we can we really trust our roadmap to get somewhere. So about products, Callisto, our emulator is actually considered a product because we have commercial applications for it. So it mimics the next generation, our future computer, and other companies also have. I'm not trying to say we are the only one with an emulator, but it's very niche actually. Not all companies have decided to put the effort into developing this, and for us, it's an important part of C12. It is hosted on the cloud. We are using 2 different companies to host Callisto, and one in Europe and the other one in the US. And for the users who want to, why is Callisto useful for people coming from the quantum computing programming side? Is because having these kind of platforms is already a way to try and test algorithms and also to develop them without having the real computer at hand. So what's the difference to other models like Qiskit? You know, the basic Qiskit, which incorporates no noise, is that Callisto is actually based on Qiskit. There, like somewhere on the, I don't really know how, but it's I think it's based on the Qiskit platform. But we incorporate our noise models developed by the theory teams, so all the quantum phenomena are incorporated. This way, we can have a direct link between the real chip that we are fabricating and the algorithmic runs. And as I said, it's built on Qiskit, so of course it's compatible with it, and also the TQS libraries and other platforms. Why do we want to try or run our algorithms on these kind of platforms? Is because it already incorporates the exact noise model. So it incorporates essentially these 3 parts: the charge noise, phonon noise, and relaxation through the resonator. We have two modalities for Callisto. Again, for the business side, it is very important for us because we offer discovery. So discovery has a bit less of computational power. It mimics or emulates an inferior number of qubits, but it already has been used by some users. But when we collaborate with people like Quantinuum or Air Liquide, we were actually using the professional version. And in every project that we do, we incorporate new features, and then Callisto Professional is.
It will be commercialized soon, right?
I mean, we are already using it for, and actually some companies are paying to use it, and also even if they don't pay, they can also act as sponsors for the collaboration, and they provide the use case. So it's already being used. Yeah, it's already being used in collaboration with other companies.
For example, for user like us, can we use Callisto or not?
That's a very good question. So anyone can access Callisto from the internet. It's for free. The discovery version is for free. You just have to go on the C12 website, and you can access Callisto. Yeah, the discovery one. And then if you're a company and you want to allocate some part of the budget, we also have the professional.
So that is the emulator, right?
It's an emulator, yeah. Yeah, and the professional version incorporates all the new features that we have developed with Air Liquide and Thales and other kinds of projects. So the enabling technologies that we use we share them really with other platforms, so I will spend not really a lot of time. Some of the critical technology we're using for the hardware and software goes from cooling to, I mean, this is very common to platforms that are trying to do the same, but basically, I think I talk about the cooling here. So our working temperatures are in the millikelvin range. So of course we need to have some dilution fridges. We are using Blue Force at our labs for different reasons, and also it's very challenging, and this is for any company really. Like any components that are used, like the temperatures are so low that the electronic specifications must comply with this range of temperatures. In terms of wiring, and again, is not my field of expertise. They need to handle extremely low temperature and high frequency, etc. So we really need, at C12, we really want to make sure that we have the best components for our workflows. Same for the signal generation, for radio frequency. I'm not going into details. For the qubit readout, we are facing the simultaneous demands of, I mean, this is also common for other companies, so limited qubit coherence time, low noise requirements. So we really need to make sure that we improve on these steps. So we are hiring. This is a picture of the offsite. The last trip we did, it was to the countryside, and we were doing activities together, like doing archery and these kind of things. And actually it was the day when I joined, because I joined like 1.5 months ago. And basically you can always go on the website, see which teams are hiring. And this is the last part, but we already get a bit I was going to propose, since I knew I was not going to be able to answer all the questions. If I was not able to answer questions, or you wanted to ask more, what I thought is that you can always contact me at my email. And if they are more technical or software related, I know everyone at C12 because we are 60 people, 65. So I can always go to them. And if you have some questions, please send it to me. Also for the internet, people who are connected on the internet. I don't know.
Thank you. So do you have any questions before we wrap up?
Otherwise, they can also send it.
No
or
worries.
LinkedIn is also fine.
No worries. So this will stay around. So no worry if you have any question. can contact them. So we will have a coffee break, like 15 minutes. We'll go back after 15 minutes.
J'entends ma prime là tourner. Mais je sais pas, il y a un truc toujours.
Avec Yann.
Ah oui, c'est ça. Bah, comme Paulin et comme lui. Alors j'ai parlé de la PFT.
Je posé la question.
Avec moi, c'est. La dernière slide, c'était. Je suis pas capable de répondre. Ah, cool, mais ça m'intéresse à apprendre. C'est juste que moi, ça fait un mois, j'ai raison. Et en plus, je sais pas ce que je vais essayer de répondre. Voilà, vraiment. Ouais, mais c'est ça, mais en plus, bon, de toute façon, mon background, c'est physique.
Ah, ok.
J'étais au CEA, mais c'est parce que j'avais fait un master en physique. Mais c'était la première fois que je faisais de la physique quantique pendant un an. Ah non, j'étais en Espagne. Et en Australie. Et je veux dire, j'ai fait les études en ingénierie en Espagne. Et les études je les fais en Espagne. Je n'ai pas tous les connaissances. Mais en fait, j'aime bien apprendre. Je pense, ouais. Mais c'est plus où. Ouais, mais déjà, si tu vas aux événements, je suis allé à tous les événements français, mais après, ça fait 4 mois que je suis au lycée Gabriel, donc je suis pas allé. C'est le premier événement français que je fais. Si ça fait 4 mois que tu es en France, je sais pas où c'est. Bah, je pense que ça a vu avant, peut-être. Je pense que ça peut-être me dit quelque chose, mais je sais plus du tout. Alors, moi, j'étais dans tous les événements, donc c'est possible. Voilà. Les événements. Sur les les événements sur les quantiques, à Paris. Ok, oui, bah, sur côté lab quantique, parce que je collabore avec eux aussi. Côté, je vois station F, candidaté. Ça, sur station F, Saclay, quand il y a eu Palais qui a fait les benchmarking pour Quantum. Ah, je suis pas allé. Je suis à l'EDF. Je suis pas allé. EDF aussi, j'étais. Bon, bah, c'est.
Il y a une équipe quantique pour voir.
Il y a les géants qui bossent sur les salles d'eau.
Ah, ok.
Pas
de l'hardeur.
Mais ouais. Ça, comment? Je sais plus. Non, il y avait un mail, je sais pas. Non, mais il était plutôt intéressé par les. Non, c'est pas les. C'était pour les. Quelque chose. Citation, c'était pour la citation. Tellement des. J'ai regardé il y a avant. Ça fait 4 mois que. Arrivé à Lane. Avant, j'étais en France et du coup, je faisais par-ci par-là des événements à Paris parce que j'étais basé à Toulouse. Et le problème, c'est que si tu montes pas ta gueule à Paris, les Parisiens disent ils savent plus que t'existes. Ah ouais. Ouais. Donc, Ah bah, c'est tout le principe de la France, hein, tout fait centré à Paris. C'est vrai, c'est beaucoup. L'Espagne, c'est moins centralisé. Et du coup, bah, je montais à Paris par-ci par-là pour dire coucou, j'existe. C'est super important. Ah bah oui, des personnes. Oui. Voilà, une raison de rejoindre le team business, la team business, c'est parce que ça. Là, c'est pour ça que je fatigue aussi. Hier, j'étais à ce Presteria parce que ma responsable, enfin, la business development team, on est business development, business tout large, on est plus 8. Mais 60. Ce que je dis, la plupart de la boîte, c'est les chercheurs. Ouais, mais t'as 10 personnes en business, t'as après de l'administratif, tu dois en avoir au moins 5. Ça réduit autant de chercheurs dans la boîte. Ah ouais, non, mais attends, je peux pas. Non, parce que moi, j'aimerais bien aussi savoir. Ça te plaît pour l'instant? Ah ouais, beaucoup. On est quoi? Non, mais en plus, dis par exemple, je te cherche autre chose. Ah ouais, non, c'est bien. Non, mais ça, tu peux couper parce que j'aime bien. Là, j'aime bien l'endroit. C'est super bien. Enfin, moi, j'étais à Saclay aussi. C'est
Hello.
Oh, that's my computer. Sorry. Go ahead.
So hello, everybody.